Hello, my name's Kevin Farlee. I'm a Principal Program Manager in the SQL Server team at Microsoft. My primary area of focus is HA&DR in SQL Server across platforms. So we're going to have a talk here about putting the puzzle pieces together, all the different facets of HA&DR, different features, different techniques, putting all the pieces together and making plans for the future. So we'll start out with, what is HADR? What's this header thing? Talk about that. It's not a single unified thing, but we'll get into that. And we'll go over the HA and DR features in SQL Server. And we'll show the progression over releases as how the HA capabilities have grown in the product over time. We'll talk about some of the new features in SQL Server HA in the more recent releases, and go through a time when we're going to talk about what to use, when, and where. So for a given situation, how would you set up an HA&DR solution for this scenario with these constraints? Talk about how to make those choices, how to make the right architectural choices. And finally, we'll talk a bit about the different platform choices. IaaS, so VMs in the cloud versus on-premise. So what's this header thing? What's this HADR thing? What's it all about? There's HA and DR. Is it all one thing? No, actually it's not. They're two distinct things. So disaster recovery is one distinct piece separate from HA. So let me explain that. Disaster recovery is recovering from an event which takes a large part of your infrastructure offline, site or regional outage. So it's not just a machine going down or a reboot or something like that. It's the site is offline. Something like that. So when you think disaster recovery, think the whole place is gone. Realistically, it's probably not. It's probably a network outage for the region or a regional power outage or something like that. But for the purposes of planning, you want to plan in terms of that whole site is gone. You can't count on anything that was there. So assume that the primary site, at least, is not accessible for an extended period. So you have no access to anything that is or was at the primary site. Communications may not be possible. You have to rely only on the resources, the people and equipment resources, at your remote DR location. Usually getting back online and available is the most important thing. You may trade off losing a small amount of data in order to get your business back online and making money. It's not that losing data is ever okay, but if your DR site was 10 seconds behind your primary site, and either you're going to wait around for 3 days to see if you can get that 10 seconds of data back from your primary site or not, or you're going to get back online right now and start making more business and backfill those 10 seconds worth of data at some later date if you can, or reconstruct. So that's what I mean by getting back online and available is more important. You're talking about getting your business back running again. So high availability, on the other hand, is maintaining services online and available at all times. So in other words, that means that HA is all about making sure that there's no interruption in the service to your customers at all. So it's maintaining the availability of the service or system with an absolute minimum, ideally zero downtime for any reason. So this doesn't mean that, well, except for when we decide to take it down for maintenance. No. It's zero downtime. It's typically represented as a percentage of possible uptime, i.e. 99.99% uptime. That's generally, you'll hear that referred to as 4 nines, and then there's 5 nines, 6 nines. You can do the math for how many minutes per year each of those works out to. There may be in your business some unavoidable downtime that is acceptable. You may have times when your business won't miss your system being down, or there may be zero down times when you can tolerate any downtime. The main thing is that any outage, Maintenance, upgrade, failure, planned or unplanned, takes away from your HA goal. So if you have a goal of 4 nines, anytime you're down for any reason counts. It doesn't matter if it's down because you planned that maintenance and so it's okay, right? No, it takes away from your HA, meeting your HA goals. So here's one chart that I came across that just charts for this company how they did in meeting their uptime targets. So green squares are up the entire period. Yellow, it had under 10 minutes of downtime. Red was over 10 minutes of downtime within that period, so within that hour. So you can see what that is. I could work out the percentage, but you get the idea of how to track it. So this is 24 hours a day. You're always looking at keeping your system up and tracking if there's any misses in that. High availability is protecting against anything that prevents an application from accessing the data it needs. So this is all about making sure your applications can always access the data that it needs. Assume the site and facilities are not impacted. That would be a disaster. Typically implemented via locally redundant equipment. So clusters where you have multiple identical machines or close to identical machines. Replicated storage. You have availability groups where we do the replication of data to multiple servers that each have independent storage. Outages are typically measured in seconds, minutes at most. And there's two metrics we look at, RPO and RTO. So that's recovery point objective, which refers to how close to the time when things went offline can you get back to. So RPO has to do with data loss. So if you recover to a point that's 10 minutes before the outage, you just lost 10 minutes of data. That's pretty bad. If you're ideally shooting for an RPO of 0. So your HA system shouldn't result in any downtime. RTO, recovery time objective, how long does it take you to get back on the air? So even if you don't lose data, if you're down for 10 minutes without losing data, that's good, but you're still down for 10 minutes, so you've just lost most of your HA. So RPO and RTO are the metrics we use to measure how well we're doing in high availability, both in terms of not losing data and in terms of continuously being online and available. So I'm going to go through a history of features, HA and DR features in SQL Server over the years. So the HA journey starts SQL Server 2000, SP4. We had failover clustering introduced. So that was working with Windows clustering. Failover clustering enables you to have 2 servers with physically shared storage. So one server at a time can physically mount the storage. So if one server goes down, or if you have to take it down for upgrades or maintenance, whatever, you just fail over the SQL instance to the other node and you're back online, even while the other node may be down for maintenance or whatever. The downtime there is typically the time it takes to start SQL Server up and get everything recovered and up and on the air. So for a failover cluster, SQL is running on one node, you shut it down, move the storage, and then bring SQL back up on the other side. So it's the time it takes to shut down SQL Server and then bring it up and run recovery on all the databases. So that's the technology that came up in 2000 SP4. Log shipping was another feature which allows you to, it's an automated system of log backup jobs, agent jobs doing log backups, and then it gets copied to your secondary server, and then there's another job that runs on the secondary server and applies the log backup, does a log restore with no recovery, so it maintains a database that's in recovering state on your secondary server, and it gets kept up to date within the granularity of however often your log shipping cycle is. So it's an early HA system, and it does give you some amount of DR because that log shipping secondary can be in a remote location if you want, or it can be across the room. Backup and restore, of course, your ultimate backstop for DR. You do your backups on a regular cadence with some pattern. Usually there's a pattern of full backups where you back up everything, and then a differential backup, which is backing up all the data that has changed since the last full backup. And then you have log backups, which is everything since the last log backup, and that's backing up specifically the transaction log data. So on a restore of a log backup, you put the data back in the transaction log and then replay it. And that's how the data gets back into your database. SQL Server 2005 was a big release. It was a 5-year release cycle, so that took a lot of time. Database mirroring came about in that time. So database mirroring is a system where it's sort of like continuous log shipping. So you have a primary and a secondary, and we had a transport that directly took the log from the primary system and piped it directly to the secondary and then applied it on the secondary. And failovers were largely, you could do it automatic, but generally they were manual failovers. So database snapshots was another innovation that came in 2005, and that allowed you to take a virtual snapshot of a database, and we would use sparse files to just collect the differences for the life of the snapshot. What that gave you is a static image of the database. So it looked like the database was unchanging for that time period that the snapshot existed. That allows you to do things like check DB without impacting your running workload. So it can be very valuable. So you don't have to freeze the state of the database in order to get a comprehensive analysis of your database. Checksum, IO validation, read, retry. So we put checksums on all the data pages. We validate the checksum on read. When we read a page in, we validate the checksum. If it didn't match, we'll retry the read to see if it was just a dirty read, and see if we can get it back that way. If it doesn't, we'll flag it, and we know that we have some corruption, physical corruption on the page. Mirrored backups and backup restore media checks. So this is the idea that you can send a backup stream to duplicate sets of media. So your backup goes to 2 different disks just as an extra safeguard, and you can also run media checks on the backup restore verify only. It would verify the structure of your backup files there. And fast recovery as a way to get the recovery done faster, get your database back online quicker. Online restores. So if you're doing restores, it allows you to do that without taking everything offline. SQL Server 2008. Have write ahead on incoming log stream. So that's a performance enhancement that allows you to do write ahead for the incoming log stream. Log stream compression. So when we're sending the log across from the primary to the secondary on a database mirroring connection, we're compressing that log stream so it makes more efficient use of the network. It's sending less bytes over the network so you can get the data across faster and be more up to date on your secondary. Automatic recovery of corrupted pages. So this is where if we detect that a page is corrupted and we'll retry the read and it's still corrupted, then we'll send a message across to the secondary and said, hey, do you have a good copy of this page? If the secondary has a good copy, it will send that page across to the primary. The primary will use that in-memory copy to complete the read immediately, and then we'll overwrite the corrupted page with the good page. So that's self-healing databases that way. SQL Server 2012. Always-on availability groups, one of the flagship HA features in the product. So always-on availability groups builds on the database mirroring technology. Some of the components are still named mirroring endpoints and such. So it has some common technologies, but it's much, much more sophisticated. So availability groups has the ability to have multiple databases in a group for HA purposes. And the idea there is that most applications commonly talk to more than one database. So you may have a configuration database or a historical database and production data. So you're going to have more than one database that all make up the greater application suite. And if one of those databases fails over and the others stay put, you've got kind of a broken situation there. So you would really like them to all move or none. And that's what Always On Availability Groups does. So we've enhanced availability groups over the years, added more and more capabilities, but the core is that you have a group of databases that will move as a unit, will automatically detect failures, and move that group of databases off so the primary role moves to the secondary server. You can have more than one secondaries. There's a lot of enhancements in that. Multi-subnet clusters. So now you can have a failover cluster in a network topology that has more than one subnet. You're not limited to having that failover cluster in one single subnet. Flexible failover policy. So here we have the ability to tune how much of a hair trigger we have for doing a failover. Failovers are somewhat disruptive. If something's really wrong, you really want to failover. But if it's a temporary glitch, you may not want to do that failover. You may want to hold off and wait and see, is it really broken? Do I really need to do the failover, or can we just pick up where we were going and without all that disruption? So now you can tune the failure level as part of the availability group configuration to declaratively say how much of a trigger you should have on your failover policy. SQL Server 2014 came along. We raised the number of secondary replicas to 8, so you can have 8 secondary replicas along with your primary. Online secondary replicas after quorum loss. So the secondary replica before this, if you lost quorum in the cluster, your secondaries went offline too, because you don't have quorum. But really the reason for tracking quorum is that you want to make sure that you never have a case where two nodes think they're the primary and start making changes that may be incompatible with each other. If they're not seeing each other, you want to make sure that that doesn't happen. It really doesn't impact read access. So there's no reason to shut off read access to a secondary just because you don't have quorum. So that's the change that we made there. Cluster shared volumes for failover cluster instances. That was a Windows failover cluster feature where Windows failover cluster has the ability to storage replication within the cluster system to present the image of a physically shared volume when what it's really doing physically is replicating storage in the same way that replicated SAN storage would. So you may have a SAN that has real-time replication to another site. Same sort of idea, same concepts. You're doing block level replication between the two volumes and presenting that as one single volume that is mounted one place or the other. SQL Server 2016, availability support, group support for standard edition. With 2016 SP1, we made a significant change in how we thought about features versus editions. Previously, the differentiator between Standard Edition, Enterprise Edition, a lot of it had to do with the richness of the feature set. And that kind of got in the way of some application development where if you had a Standard Edition, you didn't have all the same tool set that you had if you're running Enterprise. Some applications, it didn't make sense to hit the price point of an Enterprise Edition, but they needed some of those features. So it was put application vendors in a bind. So what we did is we changed it such that we have a common application surface area across all the editions, and the differentiator moved to being more in terms of perf and scale than feature richness. There are a few features that are differentiated, but for the most part the differentiation has to do with perf and scale, which is the same way it works in Azure SQL Database. The differentiation is going to be scale, performance, HA to a certain extent. They have used different HA schemes behind the scenes. So we're replicating that here, so we'll give you support for availability groups in Standard Edition that has limitations in it, and the limitations basically mirroring the surface area of database mirroring. So you're limited to one database per group, and only one replica, so a primary and a secondary. So it's 2 nodes. So it's a very simplistic way to have availability group support, but you have all that availability group technology and richness in there. And if you eventually want to scale that up because you've gotten past the prototype stage, you can upgrade to Enterprise Edition and get all the additional performance and scale. Load balancing of read intent connections. So when you make a connection into an availability group, you're connecting to a listener. A listener is an IP address that moves to whichever node has the primary role. If you're connecting, you have the option of decorating the connection string with application intent equals read-only. So if you have a read-only connection, we'll route that to one of the secondaries. Previously, it was somewhat random. With 2016, we give you the ability to do a round robin across the readable secondaries. You can specify for each secondary, if it's in the secondary role, do you want it to take read traffic, or do you want it to be just not taking any traffic at all? So you can configure all that. You've got a lot of flexibility and power in doing that configuration. And now with 2016, we'll do a round robin. So we'll get the set of readable secondaries, and we'll just round robin connections across them. So we spread the load across your set of readable secondaries. 3 auto failover replicas. So now you can have up to 3 replicas that are tagged to be auto failover replicas. It gives you more redundancy. Distributed transaction support for availability groups. So that's giving you the ability to have distributed transactions against availability groups and still have a reliable outcome. So if you're halfway through a transaction and the primary goes down, you can query the distributed transaction coordinator to find out, should that transaction have been committed, or does it need to be rolled back because it didn't get to all the participating nodes. Database level failover detection. So now that means instead of just looking at the health of the server to trigger failover, we're also going to look at the health of the component databases. So if you have an availability group that has databases A, B, and C, server is still healthy, databases A and C are healthy, database B is down. Well, that's a problem because that doesn't allow all your applications to work, so your whole AG isn't up. We'll trigger a failover to see if we can get all the databases online on the secondary. After we promote the secondary to primary. Chances are we'll be able to, and so that's what that's about. Distributed availability groups was a really interesting capability here. Think about that as an availability group whose members are themselves availability group. So it's a loosely coupled set of availability groups. So why would you want to do that? The pattern that we built that for was a geographically dispersed application that had a lot of read traffic. So think about a message posting service, bulletin board service, one of the places you go to read tips and tricks for technical stuff. And there's people from all over the globe doing those reads. The write traffic is relatively minor compared to the read traffic. So it'll be 95% read traffic, a little bit of write traffic. So the way this works is that you have one primary site and its availability group that behaves just like a regular availability group does. And you can have another availability group that's on the other side of the continent or on another continent. And it's the secondary within the distributed availability group. So that's typically going to be an async connection. There's no automated failover detection. It's not an HA solution. It is somewhat DR. It's more read scale. So here what you can do is route the read traffic to whichever replica is closest from a networking standpoint. So everything on the west side of the continent goes to that server, everything on the east side of the continent goes to that server, and all writes are routed to the primary. So we'll get into more details as to what that is. That came about in 2016. Direct seeding of availability replicas. So before this, if you add a replica to an availability group, you have to back up all the databases, restore them on the new secondary, then do log backups, log restores to get them close, and then bring them into the availability groups. And it can be a tedious process. What we do here is we've got a channel for transmitting data at good rates already in place. So what we do is we take the backup on the primary, put it over the same traffic, the same pipeline that we would send the log data through. We send the backup data through that same pipeline and then do the restore. So it's a continuous backup to piping backup directly into a restore process, and then we'll catch it up. Meanwhile, we'll buffer all the changes during that seeding process. When the seeding is done, we'll catch the secondary up so it's back in synchronous mode, and then it comes online as a valid secondary. So it's much simpler and more streamlined process for bringing a database online on a secondary. Log transport performance improvements. So we highly value customers that push us really hard. Sometimes you'd think that would be a problem, but it's really valuable to us to have customers that push our software really hard. And we've had a number of customers that push a lot of data over the log transport links. One in particular was pushing hundreds of megabytes a second over an individual link between two systems on a continuous basis. This wasn't just spikes. And they were unhappy. They wanted it to go faster so their business could go faster. Makes sense. So we took a fair bit of time, took the team that works on that transport. They went through the transport bit by bit and eliminated all the context switches we possibly could and massively streamlined it and got the performance of that log transport way higher than it had been. So now it can handle a lot more throughput, volume, and speed. SQL Server 2017. Support for Linux was the flagship feature of 2017. HA support came along with it. It's part of this product. We shipped the whole product. Full DTC support, so there had been some holes in the DTC support. That was filled out in 2017. Read scale availability groups are availability groups that are primarily targeted at providing read scale. So it's not worrying about synchronous or async, it's more worried about distributing the read traffic to multiple nodes. New cluster types came along with Linux, so now you have pacemaker, service guard, number of different cluster types on the Linux side. Required synchronized secondaries to commit. That takes some talking about. So required synchronized secondaries to commit. Without this feature, if you have two synchronous replicas and the secondary falls a little bit behind, we will allow it to get slightly out of sync for the benefit of not holding up your business on the primary. Required synchronized secondaries to commit is a way to control that. So if you have one secondary, or if you have two secondaries and you have required synchronized secondaries to commit equal to 2, you will not tolerate either of those secondaries ever falling behind your primary. So that means that if one of them does start to fall behind, we'll stop updates on the stop processing updates on the primary. So your primary workload is going to hang until the secondary catches up. So some of the engineers have dubbed that the anti-availability feature, but it's also the way to absolutely guarantee that you're not going to lose any updates ever. So for commerce type applications where each transaction represents money, yeah, it makes sense. SQL Server 2019, distributed network name support. So this is a different style of listener. The typical listener was virtual network name support, where the cluster system was responsible for moving the network address from node to node as another cluster resource. Distributed network name works a little bit different in that the listener has an IP address and a port, and the port is really the important thing. So you can have that same address resolved to multiple, same name resolved to multiple addresses. So each of the nodes within the AG would return its address, but only one of the nodes is going to be listening on that port. And it's important that when you configure that, that port is completely unique across that subnet at least. And so that way you don't have to move the address from port to port, from point to point. You just have a name that translates to multiple addresses with multi-subnet equals true on the connection string. We'll try to connect to all those addresses in parallel on that specific port. Whichever node is listening on that port gets the connection. So it works very well as a listener, but that's why it's really important that that port is unique. If you try 1433 with a DNN, it's random which node is going to pick it up because they're all listening on 1433. It's the default port for SQL. It also makes it very much simpler in Azure VMs because you don't need a network load balancer if you have DNN. So it simplifies your topology there. Azure Shared Disk Clusters. So that's a recent development where, again in Azure VMs, we have Azure disks, premium disks that can be shared between nodes. So it acts just like a physically shared disk would on-premise. So you don't have to go through file shares or other topologies like that. You can have a physically shared disk, and the shared disk gets mounted on one side or the other. So we're going to talk about each of the technologies in a bit more detail. So backup and restore, you have a primary server instance, you've got a backup job, and that sends the backup data to a backup share someplace. So that's just some vault someplace to securely store your backup jobs. Oftentimes that would be offsite. So as you see in the drawing there, one option would be to take your backups from your SQL Server running in a VM or on-premise and route the backups to a blob storage in the cloud. So you have it in a third place. In the event of a complete disaster, you still have your backups accessible in that neutral third location, whether that's our cloud, somebody else's cloud, or just another location within your corporate network. Backup and restore is clearly disaster recovery only. There's no HA functionality there. It copies the database data out to flat files. It can be done with storage level snapshots. So most SANs have the ability to make very quick snapshots at the storage level. We can coordinate with them and leverage those. And then you can copy the data off of that snapshot at your leisure, because that copy of the data will not change at all, but it takes almost zero time to create the snapshot, and then your database is back online. Backups should be archived off premises. It makes no sense to protect yourself against a site-wide disaster by keeping your data backups on that same site. Different customer site or a cloud storage, somebody's cloud, Azure or somebody else's cloud. Should be scheduled, should be tested regularly. That goes for any HA or DR technology. It's great to have it configured, it's great to have it running. Unless it's tested, you don't have a solution. You don't know if it works. So periodically do a restore. Run CheckDB. Make sure that everything's intact. Make sure you know how to do a complete restore of all the databases that make up your solution. That's really important. A lot of people get into trouble that way. Log shipping builds on backup and restore. Again, it's a set of jobs, agent jobs. So you have your primary server instance as a backup job, sends the data to a backup share. There's a copy job that takes the data from that backup share to a secondary, where a restore job restores that to its copy of the database. And you can have multiple secondaries all doing the same sort of thing. You have a monitor instance that's keeping track of status to make sure that all those jobs ran successfully every time, so you're not missing any data, not having one of your nodes that's continually failing. That's how that gets done. Again, it's built on backup and restore, series of periodic jobs. Secondaries can be put in standby to give read access. So what that is in between restores on the secondary, you can put it in a standby state, which temporarily makes the database readable. Then you have to take it back out of standby to run the next restore. Very loosely coupled system. Database mirroring has the same conceptual idea as log shipping, except instead of doing discrete backups and restores, now you have a continuous data flow from the backup on one side to the restore on the other. Actually, what we're doing is, as data is written to the transaction log on the primary, it also is written out to the network connection to your secondary, where it gets persisted in its transaction log, and then we continuously replay the transaction log on the secondary. You can optionally have a witness server, which is basically quorum. That's what gives you the ability to have an automated failover within database mirroring. It's a crude system compared to availability groups, but it's a quantum leap from log shipping. New transaction data transport. There's no separate discrete jobs. It's all controlled by the engine. It's all continuous replication. It's a per database pairing. So database mirroring relationship is this primary database to that secondary database. There's no concept of multiple databases as a group. This is where we brought in automatic page repair. So if a read on a secondary fails or shows a corruption, we can pull that page from the other copy if it's intact and automatically repair that on the primary. In full safety mode, which means basically synchronous replication, and with a witness, automatic failovers are possible. And you have unique connection strings that allow you to connect to either node. Basically, it has both the normal primary and the secondary in order. So we'll try and connect to the first one and then to the second one. Availability groups, always on availability groups. So this is the next evolution. It's another quantum leap in HA technology. So here you have an availability group where each node has a set of databases that are part of this availability group. In Windows, it depends on Windows failover clustering to do the quorum management and some of the orchestration of things like moving network names, etc. On Linux, when Linux came along, then that we're leveraging Pacemaker or other clustering systems to do the quorum management and other pieces of that. So you have your primary replica on node 1. It has its own SQL Server instance. Each node has its own individual SQL Server instance. There's a Windows failover cluster resource group for that whole set of availability group. And then you have your availability group, which has a replica on each of the nodes. Each replica has the full set of databases in the AG. Note that one of the constraints of an availability group is that all the nodes within the availability group have to be part of the same cluster. You can't have separate clusters for half of it and separate clusters from the other half. The cluster can be physically spread. You can have a wide area cluster. That's just fine. But you can't have different clusters. Automatic recover of corrupted pages. We've been through that. A replica reads a page and find it corrupted. It'll request the same page from another replica. It'll replace the corrupted copy with the clean copy from the other side, and the original read operation completes. So there's no failure that's reported to the application. It just hangs for a little bit and then completes. Distributed availability groups. It's a loosely coupled group whose members are other AGs. Loosely coupled, there's no common cluster infrastructure, good for high latency multi-site configurations. When I described distributed availability groups earlier, I neglected one of the main motivations for that, and that is with a traditional cluster, if you had a continent spreading availability group, so you had nodes in New York and LA on the North American continent, that's a long distance. And if that's a single cluster, if you lose network connectivity between coasts on the continent, which is going to happen at some point, then you're going to lose quorum in whichever site had the fewer votes. So we had one particular customer that had that scenario, and in their DR site, their remote site, they had applications that ran just on that site. They wanted to make use of the systems. It makes perfect sense. But the cluster would take them down because it lost quorum, even though there was no transactions at risk that way. That was frustrating. So what they did was, what we've done is we set up distributed availability groups. So it's an independent cluster on each site. So there's no issues with quorum from site to site across a very wide area link. Loosely coupling works in your favor that way. No common cluster. It's good for high latency multi-site configurations. So you have a primary site with a single availability group. You have a primary, secondary, and this is all one cluster. With a distributed AG, you have two different clusters and two different AGs. So AG1 and AG2. AG1 on your primary site has a primary and secondary. AG2 has an F and a secondary. So the F is the node that would be in the primary node, except it's on the secondary side of the distributed AG. So we call that a forwarder, so because it accepts updates from the primary and then forwards it to all the other nodes locally. And that also has the advantage of conserving network bandwidth on your wide area network, because if you have, say, 4 nodes on each side, instead of sending data from the primary to the other 3 nodes at the local site and all 4 nodes on the remote site, you're just sending it across to the remote site once, and then the forwarder fans it out there. So you're making more conservative use of your wide area network that way. Direct seeding, previous to that, the backup would run to some backup share someplace, and then you'd run restore to the new secondary, and then you join it into the AG. With direct seeding, we send the backup data directly from the primary to the secondary, and when the restore completes, it's online as part of the availability group. It's a very smooth process. Required synchronized secondaries to commit, we went through in a fair detail. Specifies how many replicas must be in the synchronized state. So not synchronizing, but synchronized state in order to complete transactions. If it's not met, no transactions can complete. It is the strongest guarantee of no data loss. Also the anti-availability feature, because if you fall behind at all, work stops on your primary. Failover clustering, it's a very mature technology. So you have an FC failover cluster instance, which is mounted to your storage. You see the dotted line on the other side, so the secondary machine doesn't have access to that disk. After you fail over, the connection to the disk shifts to the other node, and the failover cluster instance comes up on the other node. Storage options for an FCI: file shares, premium file share in an Azure VM, or just file shares, NFS shares. Storage Spaces Direct is a Windows technology that gives you the illusion of a single disk, or Azure Shared Disk, or physically shared disk. Failover cluster instances with premium file share. You have ease of management. File shares are fully managed by Azure. Lower work on your virtual machines. There's less overhead. You can have zonal redundancy, so you make sure that your data is stored in more than one zone. Burstable input or output. So in most cloud systems, including ours, storage is sold by, as you go up in storage capacity, it's both size as well as throughput. So to get more IOPS, you buy a bigger disk. Well, if you just need more capacity, more throughput at a certain point in time, you can burst. So you can take the data, those data volumes up to a higher level for that burst and then back down. Fully managed file storage up to 100 terabytes, burstable performance. Cons, it doesn't do host-side caching. It's a little bit lower IOPS to size ratio compared to disks. SQL Server Failover cluster instance with storage spaces direct. So this is just a diagram of this. So you have a load balancer, the SQL Server Failover cluster instance layered on top of Windows Failover cluster, layered on top of storage spaces direct, which does handles replication between the Azure VMs. So it keeps the data in sync between the VMs. SQL Server Failover cluster instance with premium file share. So this works just like a file share would on-premise. It's just that we provide all the hardware and we do the management of the file share for you. There's a step-by-step tutorial. If you pull down the deck, there's a link there. Pros, it's a fully managed file storage up to 100 terabytes, burstable performance, use AD accounts and private links. New HADR features in SQL Server. So what's new? Failover clusters instance with Azure Shared Disk. So this is a new development within the Azure storage offerings, which allows you to have the same disk shared among multiple VMs. And one VM at a time can connect to that shared disk. It acts just like a physically shared disk or a shared connection to a SAN. One of the nodes will take a reservation lock, a SCSI reservation on that disk, and that will block any other node from accessing it at all. So there's no read access to the secondary nodes. It's a very clean lift and shift deployment from on-premise failover cluster instance. Supports disk cloud file share witness. And again, you have a link to a tutorial. Failover cluster instance with Azure Shared Disk. It behaves like physically shared disk on-prem. Premium disks in all regions, ultra disks in select regions. That may be all regions by now, so that's been rolling out. No Azure Blob Cache for premium disks, so you don't have the cache for that. Shared disks are not replicated, so it's a single point of failure there. Azure FCI should use availability sets to maximize uptime, so that is a way to make your Azure resources much more redundant. Proximity placement groups is a way to set up groupings of resources where Azure will place them close from a network standpoint, so you get the least latency. So if you just create a resource within a region with no other constraints, it may be in a different data center. But with a proximity placement group, you know it's going to be within the same data center, at least in typically much tighter placement than that. Distributed network names we talked about a bit. So without that, with a virtual network name, you have to have an Azure load balancer. With the distributed network name, that simplifies that configuration. So now we're going to shift into what to use when and where. So I've gone over lots and lots of different high availability and disaster recovery features. What to use when? How do you figure that out? So Linux versus Windows HA. Largely the features are going to work the same across platforms. Windows is going to use Windows failover clustering, where Linux uses Pacemaker, Service Guard, or some other native cluster. Third-party products like DH2i can help bridge the gap and provide interesting capabilities. And containers and AKS run on Linux. That gives you another HA solution. So you have a scenario here. You have a single site. It needs basic DR. There's no stringent availability requirements, and cost is a concern. We're cost conscious here. You need some kind of disaster recovery, but solution, backup and restore. If all you need is to be able to recover from a disaster, you don't have a backup site, backup and restore. You don't need a cluster. Works on both Linux and Windows. It's a simple solution. Another scenario, secondary server is a lower tier than primary. You have a slightly relaxed recovery point and recovery time objectives. There's no impact to the workload on the primary server. You may have poor or high latency networks, and you need support for standard edition. Log shipping works perfectly. So there's no cluster required, works on both Linux and Windows, it's not sensitive to network latency, standard edition is fully supported. Another scenario, stringent uptime requirements. You can't tolerate any downtime. You need to scale out read access. So you need to have some reporting that has more performance requirements than a single node can meet. Your recovery point objective is 0, and the RTO is very low. You need fast and automatic failover, multiple databases that need to move as a unit. That's an availability group, right? We went over all those points when we were talking about how availability groups work. Read scale with availability groups, both Linux and Windows. So you have a sync or for disaster recovery, sync and DR, availability group. Another scenario, multiple sites, long distance, high latency link. Need a fast recovery time objective in the event of an outage. May need read access at the remote site. Distributed availability groups there. So you have your primary site in Boston. It has its own AG. You have fast failover between those nodes, or maybe more than 2 nodes, multiple nodes. You have synchronized DR, so that gives you a low RPO, very fast RTO. And then you have your disaster recovery site in Los Angeles that has its own AG, so you can fail over to that availability group and have your full functionality available there. Another scenario, you have an ISV solution built on SQL Server on Windows. Your company's starting to move towards Linux. You're certifying apps on Linux. Your enterprise is moving towards an all Linux infrastructure. You have rigorous business requirements. Those haven't changed. And you need a seamless migration. Cross-platform distributed availability groups are a way to orchestrate that migration. There's a lot of other migration options. Microsoft offers services to help you with these migrations. Distributed availability groups is one way to get from here to there. So you have availability group 1, which is a Windows cluster, and AG2 is your Linux cluster. You set them up as a distributed availability group so that the changes are replicated from your Windows cluster to your Linux cluster, and that way you can do your testing, do full testing with real production data, real-time production data on your Linux side, get comfortable, you know the drill, you know how to do disaster recoveries on your Linux side, you know, make sure you've got everything covered, and then you just fail over. That's your migration. Software as a service app, so a website or something. So it's a canned application from a third party. Catalog database with high volume of concurrent read-only transactions. Bottlenecks on the primary due to read workloads and increased response time. So the solution would be a read scale with availability groups. There's no cluster required, works on either Linux or Windows. There's no failover scenario, but the primary is using the AG topology to replicate out to your secondaries. And those are all available for read access. Azure IaaS, so infrastructure as a service VMs versus on-prem. Platform choices, Azure IaaS VMs can be a good solution. You can choose VM variations to your specific needs. There's a lot of different options out there, different price points, different performance points, different capability size and memory capabilities. You're not paying CapEx for the hardware. You do pay for higher spec. So if you're buying your own hardware to get higher spec, you're going to pay for more. Same is true if you're getting the VMs from a cloud vendor. So that's going to be more costly, but you're paying for what you get. On-premise servers give full control of your solution. You're responsible for availability, backups, networking, all of that. Azure VMs provide much of that for you. Lots of options and tools to use. You need to understand your business requirements, both business continuity, RTO, RPO, as well as cost. Those are business requirements, right? Nobody's got an unlimited check. Make a plan. Figure out how your system's going to work in the event of a disaster. Figure out what's going to happen in the event of a HA outage. So one node has to go down for maintenance, or you have a rolling upgrade, or one node just crashes and needs to come back up. Plan for how that's going to be orchestrated. Execute the plan. Rehearse. Practice that plan. That's critical. Make sure you have rehearsed and tested all of your plans. Otherwise, they're just paper. So, thanks to Microsoft for putting this on. Thanks for the data platform geeks and SQL Server geeks for putting this on for us. We appreciate it. Thanks for your time.